Routable sets of components are known as router states. The router will model the routable components in an application as a tree of router states. The core focus of the router is to enable navigation among routable components within an Angular application, which requires the router to render a set of components using an outlet on the page, and then reflect the rendered state in the URL. In order to do this, the router needs some way to associate URLs with the appropriate set of components to load. It accomplishes this by letting a developer define a router state configuration object, which describes which components to display for a given URL. We can use only once router module. For root in our application, because the router service mutates the browser location, which is a shared global resource. There can be only one active router service. Whenever navigation occurs within the application, the router will take the URL it's navigating to, and try to match it against a path in the router state tree. A path value that starts with a colon is known as a required parameter and will match almost anything. At any given point in time, the URL represents a serialized version of the application's currently activated router state. Changes in the router state will change the URL, and changes in the URL will change the router state. They are both representations of the same thing. The internals of the algorithms that the router uses to match a path against a route is that it uses a first match wins strategy. Internally, this is implemented as a depth-first search, with the router matching the first path that consumes an entire URL. Similar to component lifecycles, the router also has a series of steps that it cycles through each time the router state changes. During this navigation cycle, the router emits a series of events. The router service provides an observable for listening to router events. Some noteworthy events during this cycle are: 1. Navigation start. Represents the start of a navigation cycle. 2. Navigation cancel. For instance, a guard refuses to navigate to a route. 3. Routes recognized. When a URL has been matched to a route. 4. Navigation end. Triggered when navigation ends successfully. These are the steps that the router performs on navigation. 1. First, any redirects must be processed, since there is no sense in trying to match a URL to a router state until we have a finalized version of that URL. 2. The router uses a first match wins with backtracking strategy to match the URL to a router state defined in the configuration. 3. When a matching router state was found, the router then checks if there are any guards associated with that router state, which might prevent navigation. 4. The router then activates the component associated with this route state. 5. The router finishes navigation. Then it waits for another change to the router state, URL, and repeats the process all over again. In lazy loading, routes defined in the lazily loaded modules configuration will be loaded into the main configuration, and can then be matched against and routed to. Route object defines a relationship between some routable state in your application, components, redirects, etc., and a segment of a URL. A new URL tree is generated each time the URL changes. URL tree creation happens synchronously and independently from the task of matching the URL to something in the routes configuration tree. This is an important distinction because matching may be asynchronous. For instance, matching might require a router configuration from a lazily loaded module to be loaded asynchronously. Redirects simply replace a URL segment with something else, or in the case of an absolute redirect, they replace the entire URL. Internally, a new URL tree will be created, which reflects the redirect. Redirect transformations are applied to a URL before it is matched against a router state, which means that redirects are very useful for normalizing URLs or performing refactors. The router uses a function called apply redirects to process redirects. 1. Config loader. An instance of router config loader. This is used for compiling and loading any lazily loaded modules encountered along the way. You never know, the URL we are trying to match might take us to a module we haven't loaded yet. The loader will bring in the lazy module's router config. Have a look at its load function. 2. URL serializer. We've met this before. Used for transforming URL strings to URL trees and back again. 3. URL tree. The tree structure representing our URL. 4. Config. This is the routes array that we passed into for route. It is what the router will compare URL segments against. For any URL segment, the router has no idea if it should be redirected or not ahead of time, so at each route whose path matches that segment, the router checks if that path has a redirect to property. Redirects can happen at each level of nesting in the router config tree, but can happen only once per level. This is to avoid any infinite redirect loops. The path match property can be either full or prefix, and it determines how the router matches URL segments to paths. Prefix just checks that the path is a prefix of the remaining URL segments, and is the default. A value of full will check that the path fully matches the remaining segments of the URL. For redirects, full is usually used, since we often want to redirect the empty path to some other route. If prefix were used in this case, empty string will match everything, since the empty string is a prefix of every string. URL matching at the heart of the router lies a powerful URL matching engine. Without the ability to associate URLs with the appropriate set of components to render, navigation within an application would not be possible. The task of matching a URL to a route is decoupled from the behavior of the route. The routes array defined can be represented as a tree. It's no coincidence that both the objects in the routes array and the URL are represented as trees. Since the configuration objects in the routes array form a tree of router states, and since the URL is just a serialization of a router state, the URL is also a tree. Matching any URL to a router state is nothing more than matching the segments of a URL tree against some path in routes. When trying to match a URL to a route, the router looks at the unmatched segments of the URL and tries to find a path that will match, or consume a segment. Think of it as a depth-first search through the route configurations defined in the routes array. Once all segments of the URL have been consumed, we say that a match has occurred. The router service provides a property called router state, which lets you access everything about the current state of the router. The router state has two properties of interest to us, snapshot and route. Both are trees representing the current router state, components that have been routed to, along with URL segments and parameters. But they differ in one key way. Snapshot is a tree of activated route snapshot objects, which are static. Route is a tree of activated route objects, which are dynamic. The takeaway in lazy loading routes is that the router must load any lazy modules, and then merge their configurations with the application's root router configuration. Once the configurations are merged, our application can access routes inside of the lazy module as normal. Lazy loading works perfectly well whether you use Angular's just-in-time, JIT, compilation or ahead-of-time compilation, AOT. With AOT compilation, all of your feature modules will be compiled ahead of time, but they still won't be loaded into your application until they are routed to. AOT creates a ING module which has been compiled into a module factory ahead of time. This means that our application can begin using it immediately after loading it in, instead of having to compile the module at runtime. The defaults for serve and build use JIT instead of AOT. When we build without AOT, dist has modules instead of factories. This means that during lazy loading, the router will have to compile the ING module into a factory before it can be used. The only difference between the two is that with JIT the lazy module must be compiled into a module factory at runtime. Lazy loading will work regardless of when you choose to compile your application. As always, AOT will be a little faster and is usually the recommended approach. Last but not least, it's worth noting that lazy loading gets its own router guard, called canLoad. It determines whether or not a module can be lazily loaded. If it returns false, the module won't even be loaded into the browser. Note that this guard blocks all preloading. The two cannot be used together. If this were not the case, we could run into issues where the user is on a page, and in the background we try to preload a module. This activates the canLoad guard check, which could fail and redirect the user to a different page, such as login, which is definitely not a scenario we want for our users.